بسم الله الرحمن الرحيم.
Dear students, today we will go through lecture 9 of applied chemistry. The topic of discussion for today's lecture is hybrid composites. Hybrid materials incorporating different constituents are emerging as a very potential promising class of materials due to diverse but complementary nature of properties inherent of these different classes of materials. The complementarity leads to a perfect synergy of properties of desired material and eventually an end product. The diversity of resultant properties and materials used in construction of hybrids lead to a very broad range of application areas generated by engaging very different research communities. Key concepts that we will go through in today's lecture include: what is hybrid composite, different configurations of hybrid materials, properties of hybrid, applications of hybrid, mechanical strength and hybrid effect, some particular terms like stress and strain, rule of mixture, upper and lower bound limit. Hybrid composite, often abbreviated to just hybrid, may be obtained by incorporation of two or more reinforcing agents within a single matrix, or it may have two or more resin systems commonly called interpenetrating network. Difference between monocomposite and hybrid composite is a critical question. Monocomposites use one reinforcing agent and one matrix, whereas hybrid composites are second generation composites that use more than one type, shape and size of reinforcing agents or matrices to get excellent properties. Some people do believe that hybrid is different thing than composite structure. Hybrid is based on type of construction method or system used, and on the other side composite is based on materials taken into construction process. The term nanocomposite is used if the combination of structural units yield a material with composite properties. That is to say that original properties of the separate components are still present in the composite and are unchanged by mixing these materials. However, if a new property emerges from the intimate mixture, then the material becomes a hybrid. A macroscopic example is the mule, which is more suited for hard work than either of its parents, the horse and the donkey. The size of the individual component and the nature of their interaction do not enter into the definition of a hybrid material. There are 6 different configurations of hybrid materials shown in slide. The fiber by fiber hybrid composite consists of 2 or more fibers in a matrix system. The different fibers reinforce with suitable matrix for preparing the hybrid composites. Toe by toe hybrid composites are produced by combining fibers into fabric. either by weaving or by knitting. The vast majority of tows employed in woven, braided, or knitted reinforcements comprise low twist or untwisted continuous filament yarns. Three-dimensional technical textiles can be produced by weaving, knitting, and braiding. Sheets of fibers are soaked or coated in partially cured resin. The layer by layer assembly is a technique of depositing multi-layer thin films with controlled architecture and composition. Layer by layer assembly is a pervasive method for coating substrates with polymers, colloids, biomolecules, and even cells, which offers superior control and versatility when compared to other thin film deposition techniques in certain research and industrial applications. Skin core skin structure or a sandwich panel is a hybrid material made of three layers: a low density core and a thin skin layer bonded to each side. Sandwich panels are used in applications where a combination of high structural rigidity and low weight is required. Internal or external rib hybrid material is an extremely lightweight, high-performance grid-reinforced composites. The internal grid technology is inspired by leaf veins that give stiffness at minimum weight and is designed to create a rib structure on one side of a thin-walled shell element. Similarly, animals with armor brought the concept of external ribs in composites. Both these techniques are perfect for high performance applications as well as decreasing weight as per volume of the composite. It is truly revolutionary technology. Hybrid materials are composites consisting of two constituents at nanometer or molecular level. Commonly, one of these constituent is inorganic and the other one organic in nature. Properties of inorganic and organic constituents make them perfect complementary materials. By analyzing the property of hybrid materials, it should be noted that incorporation of inorganic constituent is made with a specific goal to bring or complement missing properties. Often these are mechanical strength, conductivity, optical property, electrical property, thermal property, or mass. A brief summary is outlined on slide. It can be noted that the same philosophy and property driven incorporation of organic materials into inorganic materials can be utilized for hybrid material preparation. But the difference of approach is that research in the area of inorganic utilized within organic is driven by a researcher working with organic and soft materials, while research of organic material utilized within inorganics is put forward by researchers working with inorganic materials. When designing hybrid materials, appropriate complementarity, and treatment method are chosen and utilized to the advantage of both types of materials. Overall, the choice of incorporated component would be determined depending on whether they possess required properties or not. Various modifications of hybrid materials are classified according to their applications. The diagram shows a general range of applications of hybrid materials, including biomineralization, biomimetics, retardation of flames, antibacterial properties and catalysis, fuel and solar cells, packaging and application in dentistry, sensors and membranes, release from drug delivery vehicles, cells or delivery into cells, enhancement of mechanical properties, electrical and thermal conductivity. Tuning mechanical properties is identified as a very important functionality enhanced by adding two different phases. These are inorganic and organic. Hybrid materials are tailored to match mechanical properties of required materials. In hybrids, inorganic materials are added for their hardness and brittleness, whereas organic materials are used for their softness and elasticity. So, more inorganic part means more hardness and more organic part means more elasticity. Enhancement of mechanical properties in hybrid materials by combining organic and inorganic parts have been shown in figure. Hybridization with more than one filler in the same matrix provides an other dimension to potential versatility of composite materials. Hybrid composites have greater possible control of specific properties, achieving a more favorable balance between the advantages and disadvantages inherent in any composite material. Thus, for example, by combining two types of fillers, a reduction in modulus will bring increased fracture resistance and reduced cost for the composite. Quantitative description of hybrid composite behavior affected by the amount and type of hybridization is of considerable interest. A positive or negative hybrid effect is defined as a positive or negative deviation of a certain mechanical property from the rule of mixture behavior. In this system, both the mechanical properties of the filler and interface which they form with the resin are entirely different. In material science, a general rule of mixture is a weighted mean used to predict various properties of a composite material. Rule of mixture is a method of approach to approximate estimation of composite material properties based on an assumption that a composite property is volume weighted average of matrix as well as volume weighted average of dispersed phase. It provides a theoretical upper and lower bound on properties such as elastic modulus, mass density, ultimate tensile strength, thermal conductivity and electrical conductivity. An upper bound limit is the maximum theoretical value for a particular property, whereas lower bound limit is the minimum theoretical value for a particular property. Every component in system experiences some form of loading due to applied forces. Reaction of every component to these loads are described by its mechanical properties. When components are subjected to tension or compression, the mechanical properties of stress and strain determine whether component can withstand the load or not. Stress is the force applied to a material divided by material's cross-sectional area, whereas strain is the deformation or displacement of material that results from an applied stress. The most common way to analyze the relationship between stress and strain for a particular material is with a stress-strain diagram. Stress-strain diagram provides valuable information about how much force a material can withstand before permanent deformation or failure occur. Many materials exhibit a proportional relationship between stress and strain up to certain point, referred as proportional limit, shown as point A. This stress-strain relationship is known as Hooke's law, and in this region, the slope of stress-strain curve is referred as modulus of elasticity or Young's modulus. It is denoted by E. The modulus of elasticity is essentially a measure of stiffness and is one of the factors used to calculate material's deflection under load. Just beyond the proportional limit is the elastic limit, and at this point the material transitions from elastic behavior to plastic behavior. For many materials, the proportional limit and elastic limit are same or nearly equal. The stress-strain curve shown here contains proportional limit and elastic limit equal. The elastic behavior is the behavior of material where any deformation due to applied stress is reversed when the force is removed, whereas plastic behavior shows irreversible deformation even after the removal of stress. The yield point, shown as point C, is the point where strain increases faster than stress, and this point is referred as strain hardening, and the material experiences some amount of permanent deformation. For materials that do not have a well-defined yield point or whose yield point is difficult to determine, an offset yield strength is used, shown as point B. Offset yield strength is the stress that will cause 0.2% permanent strain. It is found by drawing a line starting from 0.002 of x-axis, which is actually strain axis, and runs parallel to stress strain line, which is slope E. The point where this line intersects the stress strain curve is called offset yield point. Finally, at point D, where the curve begins to fall, the material's ultimate tensile strength has been reached. This point denotes maximum stress that can be applied to a material in tension before failure occurs.
Nano and smart materials are all the rage, and material scientists have been rubbing their hands at the new breeds of amazing materials they've been able to create recently. Of course, these materials only seem to defy the laws of physics, rather than break or violate them, because obviously, we can only ever create anything within the laws of physics. But some have genuinely changed the way we think about the physics of materials and their properties. Number 10. Terminator polymer. Cut this polymer with a razor blade, and it will glue itself back together in a matter of hours. Okay, so it doesn't exactly move back into form on its own. You have to push the pieces together, but still, give it a while and it'll feel like it's never been cut. Dubbed the Terminator polymer, this crazy material is aptly named after the self-healing material seen in the Terminator movies. Material designers have always sought a strong, hard, and versatile material, which can fix itself on its own. But before this material was created, self-healing plastics would need a stimulus in order to instigate the healing process. For example, certain plastics would repair themselves when heat is applied to them. Contrastingly, this plastic self-heals at room temperature and does so spontaneously with 97% efficiency, meaning 97% of severed bonds will actually repair. This is achievable through the use of aromatic disulfides, which react and bond at normal temperatures. Number 9. Hydrophobic materials. You may have used waterproof spray on a tent or on your shoes or boots, but then, when it really buckets it down, it tends to fail pretty quickly. Creating waterproof sprays is no easy task, but it's a lucrative business. Neverwet has made the first stab at dominating this market with a super hydrophobic sprayable coating that can waterproof almost anything to a depth of a few foot. Not only can it waterproof all manner of items, it also protects them against corrosion and is functional under extreme heat or cold. Neverwet adheres to almost anything, and it's widely available for a whole host of industrial and practical applications. Another liquid problem solved with smart materials is getting those dribs and drabs out of a sauce bottle. Scraping the inside of a glass bottle or container for the very last drips is frustrating and wasteful. The solution? Coat the inside of the bottle with a smart frictionless material that allows the contents to just slide out freely. These liquids could also reduce friction in oil, water, or gas pipes to prevent clogging. The only downside is that you might end up emptying half a pot of mayo onto your dinner. Number 8. Gallium. Gallium is one of only 4 metals which are present as liquids at temperatures near room temperature. The others are mercury, rubidium, and cesium, and their most familiar use is in thermometers. Gallium is a beautiful metal. It's soft and silvery, and has a melting point of just 29.8 degrees Celsius, meaning it will easily melt in your hand. It boils at 2,229 degrees Celsius, which is quite high. There's a massive gap between its melting and boiling points, when contrastingly, mercury boils at just 356.7 degrees Celsius. Unlike mercury, gallium is perfectly safe, meaning you can handle it without worry. This also means it's occasionally used as a replacement for mercury in medical thermometers. Gallium is also alloyed with other metals to create brilliantly bright mirrors. It just goes to show that even the elements of the periodic table have seemingly strange properties on their own. Number 7. Smart bendable wood. Wood will always be a premier building material due to its beautiful aesthetic qualities and versatility. Generally, wood is rigid, but now, bendable wood allows us to flex wooden structures into spaces to create stunning interiors which are durable and possess extraordinary sound absorption properties. Ducta is one such company, pioneering bendable wood, which possesses strength with amazing flexibility. Because of Ducta's density combined with its layered form, it's an awesome heat and sound insulator. This wood is manufactured from either particulated wood blends that are mixed with flexible glues, or from carefully adhering flexible wood sheets in patterns which allow for flexibility. Number 6. Vanta Black. Have you ever considered how some blacks look much, much darker than others? One of the darkest places on Earth might be inside a deep cave, but now we can view super dark blacks above the Earth's surface. The blackness of a color is determined by how much light it absorbs, and thus how little reflects back into our eye. The more light absorbed by a colored surface, the darker it will be. Even very deep blacks reflect some light, though, and it's theorized that a black hole is one of the only objects in the universe that lacks any light at all. Obviously, the darkness of a black hole isn't readily observable, but Vantablack gets pretty close. Vantablack is a black so dark that it looks like how you'd imagine a black hole would look. There is no reflection, no color, just nothing but darkness. Even on computer screens, it looks rather strange, much darker than the blacks we're used to seeing. This black is made from very densely packed carbon nanotubes, and it absorbs a massive 99.96% of all visible light. The artist, Anish Kapoor, famously seized exclusive rights to the original Vantablack color, but the recently created Vantablack 2.0 is even darker. Number 5. Line X. Smart materials in cans. It's a big theme in the 21st century, and Line X's spray paint offers a method of making virtually any object far more durable by simply coating it in a spray. Once sprayed, Line X forms long polymers which bind to the surface of the object, encasing it in a solid plastic. Line X is used to prevent the splintering of plastic car parts, but can also be sprayed on other surfaces to help them absorb shock and prevent shattering and splintering. Line X is used on the walls of the Pentagon to reduce the chance of shrapnel penetrating the building in the event of an attack. Line X's ability to strengthen fragile objects has been demonstrated with plastic cups that can withstand a human's weight after being sprayed. Eggs coated in Line X can even withstand drops from great heights. The uses of Line X are pretty unlimited. Anything which is prone to shattering, cracking, or splintering is easily strengthened with Line X, and it's incredibly hard-wearing and weatherproof to boot. Number 4. Supercooled rubidium. So here's a material which really does seem to defy physics, specifically Newton's second law of motion. Newton's second law says a force is equal to the mass of an object multiplied by its acceleration. These forces are exhibited in the direction you expect. So, for example, when you push a door, it opens outwards in front of you. Supercooled rubidium, created by cooling rubidium to near absolute zero, reverses Newton's second law. When you exhibit a force on supercooled rubidium, it seems to actually push the opposite way. The physicists themselves were baffled. "It's very counterintuitive and weird," said John Butterworth at UCL London. Others suggest that the analogy some use to describe this effect is a bit off. While supercooled, rubidium does seem to behave like a material with negative mass. The atoms don't literally weigh less than zero. Number 3. Hydrogels. Some advanced hydrogels are mechanical metamaterials which flow like liquids, meaning they can be poured into cavities. It then solidifies whilst remaining highly absorbent. The primary use of hydrogel is in medicine. Hydrogels can be inserted into wounds, and then drugs can be absorbed into them. Some hydrogels are made from long-strand polymers, but the very last have been created organically from DNA. One highlighted potential use of hydrogels is to deliver drugs to areas where tumors have been removed, but cancer cells remain in the surrounding tissues. Hydrogels would conform to the cavity, and anti-cancer drugs could be delivered to surrounding specifically affected tissues. Number 2. Starlight. Starlight is by far the most mysterious material on this list. Firstly, it wasn't produced by any scientists, but instead by an amateur inventor named Maurice Ward, who was a forklift driver and ladies' hairdresser from Blackburn, UK. Ward claimed to have invented a remarkable material that could insulate anything from extremely high heats. In fact, some tests claim that starlight could withstand temperatures of over 10,000 degrees Celsius. Ward essentially cooked this up in his own house and used it in his hairdressing business before realizing quite how effective it was. After mailing top chemical companies with requests to demonstrate the product, he was finally invited onto the BBC science program Tomorrow's World in the 1970s. The presenter famously blowtorched a raw egg for an amazing 5 minutes at 1500 degrees before demonstrating that it remained completely raw inside when cracked. Ward's material finally attracted attention, and even the NASA spokesperson at the time seemingly verify the authenticity of starlight. We have done a lot of evaluation, and we know all the tremendous possibilities that this material has. Ward had achieved something that decades of intense research could not, and his material would be incredibly useful in many industries. Rumors suggest that starlight went black, meaning it is safeguarded by governments to prevent it from being replicated. Starlight is so resistant to heat that it could safeguard objects from nuclear blasts. The truth is, starlight and its current status is still a bit of a mystery. Number 1. Aerogel and SF6 gas. When aerogels were first developed in the 1960s, they were seemingly strikingly defiant of traditional material physics, with extremely low densities and extremely low thermal conductivity. They are porous materials that were nicknamed frozen smoke due to their rather ghostly appearance. Aerogel is more of a foam than a solid, but it's still capable of holding 3D shapes. Despite its remarkably low density, 150 brick-sized blocks of aerogel will only weigh as much as a gallon of water. The coolest property of aerogel is its heat-insulating properties. Experiments show how even a small sheet of aerogel can insulate something delicate like a flower from the heat of a flame. Aerogel has been employed by space agencies like NASA as a super light insulator. It can be packed into spacesuits or used as cavity insulation for spacecraft. Sulfur hexafluoride, on the other hand, has a rather contrasting characteristic of being very dense for a gas, about 5 times denser than air. It's non-toxic and inert, meaning it can be employed freely as a gas insulator for electronics. This also means you can safely breathe it from a balloon to observe the super low pitch of your voice created by the gas's high density.
Sulfur hexafluoride.
Smart materials that open new avenues for scientific understanding and practical applications and are constantly developing. There are probably many highly advanced materials in research and development right now, and many may yield fantastic benefits for humanity. Which material did you think was the coolest and more revolutionary? Let me know in the comments down below. Thanks for watching.